We're going to work through the solution to this homework problem for process dynamics and control. It's to simulate the spread of HIV infection in a person. Okay, so we have, if you come to the APMonitor.com website and then /PDC for process dynamics and control, and then come down to the assignment section, and you'll be able to find this right here under the simulate HIV infection. And this is an exercise in being able to simulate this dynamic system. We have three differential equations right here, and we have a number of parameters. Okay, so let's just start working through this. HIV spreads and can develop into AIDS, and AIDS can lead to immune system failure and eventually inability to defend the body against infection or cancer. Okay, so without treatment, bad things happen, and survival time after infection is typically 9 to 11 years, depending on a number of factors. And but now with antiretrovirals, these patients with HIV can live healthy lives much better than before. And so it's almost like there's a functional cure for AIDS. Okay, so we have this dynamic model. Now this comes from a literature source, and we're just going to try to replicate it in Python. And we have some initial conditions. I just kind of skip down to the solution there. Let me do that again. Okay, so there is the healthy cells, the infected cells, and the virus count. So initially infecting the individual with 100 virus count, and this is very low on the number of cells, so not really realistic there, not just 1 million. You have many more cells than that, but we're just going to do that for this case. Okay, and we have a balance equations for the number of healthy cells. So we're going to start off with 1 million of these and 0 infected cells. But as you'll see with these balance equations how that causes the number of infected cells to increase. And then you have the virus as well. So you have 100 of these. They are going to, anything that is in blue means that it's going to make that that quantity larger. Okay, and anything that's red, there's a negative sign there. It's going to cause the derivative to be more negative, and it's going to cause it to decrease. Okay, so let's just go through some of these terms just so we can understand them. There are six parameters in our model, and I'll make this just a little bit smaller so we can see a few of these. Okay, so KR1, okay, and you see that right here, and that's just the new healthy cells per year. Okay, so the time basis for this is years, so DT is going to be in years, and this is going to be the number of just healthy cells that are being produced every year. Now we also have KR2. Okay, so you see this is going to be a negative term right here. The KR2, that is going to be the death rate of the cells. So we're going to say that about 10% of them die every year. So 0.1 on KR2, that's going to be the rate at which they are dying. So we have about 100,000 new cells per year. So about, for a healthy individual, you're replacing the cells with new healthy ones, and it's about the same rate at which you're losing them. Okay, so there you have those two. And then KR3, that is going to be the healthy cells converting to infected cells. Okay, so we have this term. Now here we have two terms that we're multiplying by each other. This is the virus count right there, multiplied by the healthy cells times by this KR3. So the more virus we have, the more healthy cells we have, the more of them are going to be converted into infected cells. And so you can see this same term replicated right here. So what you're losing from the healthy population, it's going into an infected population. So you're basically just taking a piece of that and moving it down into the infected. Okay, and then you also have another term here on the infected balance right here, KR4. and that's the death rate of infected cells. So about half of those die every year. So that's more than the healthy cells. Healthy cells only lose about 10% per year, but the infected cells, those just have a higher death rate. Okay, they're infected with a virus. They're pumping out these additional virus, and so these infected cells are going to die at a much faster rate. Okay, so I think that's what that parameter tells us. Okay, and then we also have this same term right here. Okay, so this is in all three balance equations, and what's happening here is a virus is going into a healthy cell, and then the healthy cell plus the virus is going to become an infected cell. Okay, so you consume a virus when you infect a cell, and so you can see that that is a negative term. It decreases that quantity. Okay, let's go on to KR5 and KR6. The death rate of the virus, okay, just at the rate at which they're removed or become ineffective. Now that is very high, much more than the healthy cells or the infected cells, 10 times the infected cell rate. Okay, so these virus, they're going to be removed or become disabled in some way. Okay, and then KR6, this is the one that makes the virus spread through the body. It's the production of virus by infected cells, and that is equal to 100. Okay, so that is a parameter equal to 100. This one is 5. And so if you have an infected cell, every year we're going to claim the infected cell is going to make, at the rate of 100 virus per year. I guess you say viri, or the plural of virus. Okay, so there you go. You have these balance equations. You want to look at these a little bit and basically think about, we have accumulation. Accumulation on the left is equal to in minus out. Okay, so that's what you do for all of these balance equations. That's why any of the in terms, or generation plus generation minus consumption. Okay, so anything that causes that accumulation to increase, it's going to have a positive sign. Anything that's going to cause it to decrease, it's going to have a negative sign. Okay, so we have these three differential equations with some parameters that we know about already, and we want to be able to simulate this over the 15 years. Again, they said 9 to 11 years if there's no treatment. We're just going to assume that this patient's going to last about 15 years. And let's say we just had some data from a patient. The doctor just plots that data here, and then we have our model prediction where we're going to try to match up with that. Okay, so typical lifespan of a patient would be 9 to 11 years. Okay, and with antiretrovirals, we might be able to extend that a little bit more. Okay, so there are the differential equations. And what we want is a semi-log Y plot that shows the progress of infection as the sketch above, and discuss what terms you would adjust to match the HIV lab data. So let's say you had this lab data that measures the virus in a patient. And then the third thing we're going to ask is, suppose that a new antiretroviral drug is evaluated in clinical trials, the virus count data is collected over many years. Discuss what terms could be added to the differential equations to include the effect of an antiretroviral drug. Okay, so a couple of references here. This is where the model was taken from this book. And there's just a couple links there where we do some other things with this, and some student groups have done this for their project in the past. Okay, so let's go ahead and get started with this. We're just going to go ahead and start with these differential equations right here. I'm going to remove some of these circles. Okay, there we go. We'll just start with those, clean it up just a little bit. And I'll go and move this over here, just so we give ourselves just a little bit more room. and we're going to use ODE int to be able to simulate this. And so I'm going to, I'm just going to do this in Notepad++. I won't download the update right now. Okay, there we go. And I will save this. I'll save it. Okay, so I'm going to save this to my desktop. Okay, so this is going to be HIV simulation, and when I save it, it's going to let me save it to my desktop, and I'll just call this HIV sim.py. Okay, here we go. So we're going to need to first of all create a new function, and so I'm going to define HIV, and then we have to have our states for the function. So I'm just going to say that's x, and then our time value. Okay, and inside this function we can include our differential equations, but let me go ahead and break down the different states. We have our healthy cells, and I'm just going to say that's my first state. My infected cells, that's going to be my second state, and then my virus is going to be my third, and then my DHDT is going to be KR1 minus KR2 times H minus KR3 times H times V. Okay, there's my first equation right there. And then DIDT, okay, the infected cells. I kind of use this term over and over again, so I'm just going to define this one up here. Okay, I'll define that as my parameter P minus P, and then plus P minus KR4 times I. Okay, and it does cause this autocomplete thing, so I'll get rid of that. Okay, and then dVdt equals minus P minus KR5 times V plus KR6 times I. And it keeps doing ID. Okay, so then I need to return three things: DHDT, DIDT, and dVdt. I'll return that as a list. Okay, and then what I need to do is I have this function. Let me just go ahead and test out this function now. So I'm going to test it out. I'll print, and let's go ahead and print HIV with an input of, let's just give it the initial conditions, 1e to the 6th, 0, and 100. So let's evaluate our derivatives right at the beginning at time 0. Okay, so let's have a mismatch in parentheses there. I'll go ahead and save that, and now this is on my desktop. I'll move this over here. Okay, and I'll run this. You can either run it in Jupyter Notebook, or you can run it, with IDLE. Okay, and if you run that, let's just see if we have any errors here. Okay, list is out of range. Oh, I did a 3 there, and it should have been a 2. Okay, and let's go on. KR3, okay, I haven't defined my parameters yet. Yes, I need to do that. First of all, I can do that outside the function, or I can do it inside the function. Okay, I'll just do that inside the function, KR1. Okay, let's go over here and just define the values of those. Okay, 1e to the 5th, KR2. Okay, so just go and type all these in. And 2e minus 7, so it's 2 times 10 to the minus 7th. KR4, 0.5, and 2 more. Okay. KR5 is going to be 5, and KR6 is 100. All right, let's go ahead and run this one more time and see what it prints out. Okay, so there are my derivatives. There's DHDT, DIDT, and dVdt. So you can see immediately that the healthy cells is going to be decreasing at a rate of about 20 per year. The number of infected cells is going to be increasing at about 20 per year. And the number of virus count would be decreasing at minus 520, okay, because that goes into converting over to the infected cells, and it also goes into because it has such a high removal rate of this virus. Okay, so there we have our function. Okay, and now what we want to do is simulate this. I can go ahead and take away this, just testing that my function worked, and return the derivative values. And now I want to give it some initial conditions, 1e to the 6, 0, and 100. Those are going to be my initial conditions. I want to have some times where I want to define this. So now I need to have numpy. So I'll go ahead and import numpy. And let me convert back over to Notepad. It's just a little easier to see. And I'll reload that and just move it right over here. Okay, a little bit bigger font. So now I want to do import numpy as MP. I know I'm also going to need my ODE int as well. So I'll import scipy.integrate. I'll do from. Just make it a little bit easier. From scipy.integrate import ODE int. Okay, so now I have ODE int there. That's normally scipy.integrate.ode int, but I just imported just the ODE int function. And then I'm also going to need to plot this eventually. So I'll import matplotlib.pyplot as plt. Okay, so I have all of those, and now I need to define linearly spaced values between 0 and 15. I'll do 1,000 points just for now. Okay, so now I have 1,000 points, and now I can use my ODEInt function. Okay, ODEInt. And if you forget how this works, one of the things you can do is just do help ODEInt, or if you're in the Jupyter Notebook, you can, or I guess in Spider, you can do Control-I for information about that function. So you just hover over it as you type it, and then Control-I, and then it'll pop up as a help. Okay, and what you'll see from that, if you do the help on that, is you'll see that it needs to be the result, okay, is going to be equal to ODEInt, and then you put the function name, that's going to be HIV, and then we're going to do the initial condition and then the times that we want to see the solution at. Okay, so here is our, here it is, and then it's going to produce 3 columns of results, where basically it's going to be, the first column is going to be all of our healthy cells, the second column will be our infected cells, and the third column will be the virus. And we'll have our time, okay, and then so we'll just want to plot the time versus the healthy cells, or the time and the infected cells, and time and virus. Okay, so we'll plot each of those combinations and just extract those columns. Okay, so let's go ahead and do that down here below. We'll just say healthy cells is going to be just my first column, and my infected is going to be my second column, and my virus will be my third column. I keep doing 3 there. Okay, and then now I want to create a new plot, and so I can just do plot and T comma H. Okay, and now this is going to be not a semi-log. So you can see here, this is kind of like the semi-log Y. It's going to be increasing so fast, so rapidly that it starts off at 100 right there. It looks like it dips down a little bit, but then it's going to increase to 10,000, 100,000, a million. So it's going to be increasing pretty quickly. We want to be able to see that a little bit better. So let's do, instead of plot, we'll do a semi-log Y. Okay, and let's do that for I and V. Okay, I and V, and then we'll show it. Okay, so you don't need to do show if you're in a Jupyter Notebook. Okay, so now I'm going to just close this out, and I'll open it up back with IDLE so I can run it. And when I run, let's see what it comes up with. Okay, so it's going to take a little bit. I've got 1,000 points where I requested the simulation to go for 1,000 points, and I can see I've got something that looks very much like the plot that you see on the right. I can also change the style of those. Okay, you can format that. So we basically have the plot. Let's just go on to the next one. You can format that. Dashed lines or other things. Label it. All the things that make the plot look nice. Okay, so let's go back to our questions then, because there's some really important questions and some insights that we can get from this simulation. So we want to have the semi-log Y plot that shows the progression of the infection. Discuss what terms you would use to match the HIV lab data to the simulation. So let's say we're a little bit off. Let's say this were too low. It's predicting that the virus was going to increase like this and kind of level off, but you see all of your measurements that it should be increased. So what terms could you adjust in your model to make that more match better with the data? So maybe something like let's see, let's look at some of the virus count ones. So we might make this one just a little bit larger, the KR6, or we might make these terms that take it away a little bit smaller. The other thing we could do is strengthen, let's see, KR3. That would affect this term, and that term. Basically turn the body into this much more susceptible to growing these infected cells. The infected cells are going to produce more virus. So there's a couple different ways you could do it. You just want to look at the balance equations and figure out which one should be adjusted up or down. Later in the class we're going to use something called optimization. We're going to develop something like a sum of squared errors for those predictions, and then adjust the parameters to minimize of sum of squared errors. So that'd be another way to do it. Okay, and then there's another question here. Let's look at that one. So let's say there's an antiretroviral drug that's being evaluated in clinical trials. You don't want to use too much or too little. You want to kind of find the right amount to use for the patient. Maybe there's some side effects to the drug, or maybe the drug is very expensive. Okay, and you want to be able to have it be used by more people. It's a limited supply, for example. Okay, so what terms could be added to the differential equations to make this so you can simulate how effective an antiretroviral drug would be? Okay, so let's look at that. Okay, so if you had an antiretroviral drug, let me just say, let's do another. Let's see. So that would be kind of like an input to the system, like you'd be injecting the individual or having them take these antiretrovirals. And so what would that do? Does it bind? Does it kill the infected cells? Does it bind to the virus? Let's say it binds to the virus and makes the virus ineffective. Okay, so then you might have another term here, like a KR7 times an antiretroviral injection or something like that. Okay, and that would decrease the amount of virus and allow you to simulate the addition of this drug into the system. Okay, and so you'd come in here and add another term like KR7 equals 1, and then you would have, let's just say, if time is greater than, let's say at 3 years, they say, oh, let's start giving this patient some antiretroviral drug, and then our antiretroviral A is going to be equal to 10, and else is A is equal to 0. Okay, so at 3 years, they start treating this patient, and then you would add a term like minus KR7 times A. Okay, so let's run this again and see if that's enough to help the patient. Okay, didn't do a lot. So we might have to increase the dose. I'm going to increase it by 1,000, and maybe we didn't catch it early enough. Maybe it's already, okay, so that maybe not enough there. Let's keep going up. We need a lot of antiretroviral. Our virus is really spreading fast. We have a lot of infected cells. Okay, so I'm going to just increase that kind of to a very high value, and ooh, that one kind of went unstable there. Oh, you know what? That one made it go all the way negative. I think I need to have times V here, because as the virus goes to 0, the virus shouldn't go negative, for example. Okay, so let's tame that just a little bit. Okay, I'm going to go back to 10, because I probably messed that one up. Okay, so I'm just kind of, working with it, seeing if I can get a good result. Looks like we had another warning here. Some problem with the simulation. Oh, I had double scalars. Okay, so I had a warning or an error. Let me see if I can go down to that one. Okay, V is not defined. Okay, I have a capital A there, but it's lowercase v, and so it stopped working. Run it one more time. Okay, so you can see that the antiretroviral had an effect at 3 years, maybe not enough. Let's increase that to 100. Okay, so you can see the process here of, adding this additional term. I really don't know what it is, but what it should be. But there you have kind of a functional cure that I've added by treating the individual at year 3, and it causes the virus count to decrease, to be in control. And so you could simulate a lot of things with once you have a numerical solution, you can, and these differential equations that describe the individual, you can start thinking about, how can I match up this simulated system to an actual person? And then once you've matched it up to an actual person, what you can do all sorts of what if scenarios, like what if I gave this individual a treatment at this time or this dose, and then you can immediately start seeing the value of doing that, because you have a system of differential equations that represents the cause and effect relationship for that individual. And that's very powerful. That's exciting to be able to think about, be able to help people by doing this in simulation first and not having to test it out on individuals like in clinical trials. So anyway, this is I hope you've learned a little bit from this exercise, how to simulate these 3 coupled differential equations, do some what if scenarios. I'd encourage you to change the parameters, see the type of sensitivity there is to these different parameters, and really try to understand this system of differential equations and how to simulate it.